Hello everyone, I want to talk a bit more about how to optimize ships that have a fixed power plant and are using that for thrust. So we're talking about fission reactors, fusion reactors, antimatter. It sounds futuristic, but NASA is currently working on a fission-powered ship, so it is time. And I previously introduced this power limited transfer calculator. It's available on my website, and I'll put the link in the video description. It has since been improved. So this is version 9. Make sure if you've accessed this before, you refresh and make sure you get version 9 in the address bar. And this version changes the way the trajectory is calculated. I bounced back and forth with Claude and ChatGPT and improved upon it. So now it's got a more realistic trajectory when you pick your departure date. You can't see me select the date, but there's a dialog here. And then calculate, and it'll set the distances appropriately depending on what you pick. So that's all good. Now, this is only valid for bacistrochrone trajectories, which means that you're accelerating for half the trip and decelerating for half the trip. So it shows you the peak cruise speed. That's the peak speed that you're going at. I'm still not sure whether it's properly adding in the velocity with respect to the sun. So, because we have existing paths around the sun, we have the initial velocity that we get going out of the Earth system and stuff like that. We don't start at zero, in other words. So I don't know if it's building that in or whether that should be added to this. But in any case, the trick here is that if you're using that kind of trajectory where you're accelerating and decelerating each for half the delta V, and you're just constantly doing that instead of having a long coast phase, then you only have a limited amount of time to do that burn. So in this case, the trip time is 324 days. And so you can iteratively solve for the thrust. In other words, if you've got 324 days, you can then say, okay, well, then we only need 240 newtons of thrust to get there. And the thing is that if we can minimize the thrust, we can maximize the ISP because the jet power produces a trade-off between those two. You can't increase both at the same time unless you increase the power. If you add more power, definitely not zero. If you add more power, then you can increase both at the same time. See, they both go up. But there's no way that you can have both go up at the same time with a single power plant. And so given the trade-off, we can say, okay, well, we are going to solve it so that we get just enough thrust and we have the best possible ISP, and then that has an effect on how long it takes for us to burn the fuel, so it has to iteratively go through all that to get the answer. Fortunately, it doesn't take too many iterations to solve it. So we get this solution, and the thing that I sort of made this calculator to do was to answer a supposition of mine. I had looked at the equations myself, and I had thought there was a way to optimize for the trip time. So if we increase this, now we have 10 times the initial mass as the final mass here. So we've got a mass ratio of 10. The trip time is 346 days here. But if we had less propellant, the trip time was less. Well, that's because we're carrying more propellant that we can't use, which is slowing down our acceleration. So that is the realization. So there has to be some point where we hit a minimum, we hit an optimal stage time, because, of course, if you only have a little bit of propellant, you're got to take a long time because you just can't accelerate to as high a speed. So you get this situation where as you increase the propellant, your trip time gets lower and lower until a certain point where there's just no way to use the propellant. And then it's just slowing you down. So, actually, initially, Claude did not understand that this was a thing and tried to say that there was no minimum. But that is because it was mistakenly varying the final mass, the dry mass of the ship. We don't want to vary the dry mass of the ship. And so I had to produce this graph. And we see here that we hit a minimum at around 4. It says interior minimum at exactly 4, even though it says 4.01 here. It's just rounding. And The first time I went through this, it actually found the minimum at 2.87, so over here. You can see that it'd be pretty close in terms of the trip time. It's only like a few extra days at this point. And that was artifact of how it was calculating the trajectory. I brought the calculator back to ChatGPT and said, is the minimum really at 2.87? It said, no, you're calculating the trajectory using an approximation. Get rid of the approximation and you'll see it's 4. By the way, the dot at 4, because this is a logarithmic scale, isn't quite between 3 and 5. That's because this scaling is not evenly split. Okay, so that the result is that we now know that for any ship, we should be going with a mass ratio of 4. So that means that the initial mass is 4 times the final mass, the dry mass. So then we hit optimal trip time. And it doesn't matter which one it is. So going to Uranus, the minimum, the trip time changes, but the minimum is still 4. And you can just plug in whatever numbers you want here. You can see right now at 4, it's 1.86 years. Here it's 1.87. Now it's not much of a difference, right? Down here, you can go from 2.8 all the way up to 6 or 7, and you wouldn't notice any difference at all. If you want a lighter weight ship, then you can manage it and still get the same trip time. So you can reduce the amount of fuel. So, I mean, even though the optimal would be 80 tons here, 1.86 years, you could get all the way down to, say, 60, and it's just 0.02 years more for this amount of power, right? So it depends on the power and the distance. So for any given distance between yourself and your target and your power, we will be able to determine what your ISP is supposed to be, what your thrust is supposed to be, and more or less what your ship is going to look like in terms of how much propellant it's going to carry, and also how much time it's going to take you to get there. So the things that we absolutely need to plug in then is just the power and how long the trip is. That's it. The power and how long the trip is the necessary thing, and other than that, the nature of your ship, I mean, if it's bigger, you know you need to increase that too, so that it ends up with R equals to 4. So that's R equals to 4, and we calculate 3.18 years, and then we get, that's the ISP you should have, and that's the thrust you should have, assuming you want to continually burn. So continuous acceleration towards, and then slowing down. But this is a straight line model that ignores the sun's gravity. It sort of tries to do certain things to help, but it's not perfect. But the principle is interesting. The principle is our ships are a certain size. And you know that if your ship is not that size, it's not doing exactly the right thing. If you're using this kind of trajectory again, of course. But as we have the high-powered far future engines, and of course I've nerfed those, this becomes much more important to optimize those trips. So if we have 100 megawatts here, we can get 1 kilonewton. But, you know, that's what it ended up being, right? We had those, when I looked at the far future ships, it turned out that a lot of them needed their thrust a little bit nerfed. But if this is all correct, then that's not as big of a problem. Now, on the closer in situations, note that we are picking an arbitrary date here. So there's an orbital matching between Earth and Mars here. You can minimize that, right? That means that it's not the optimal window. So for instance, in this case, and you can't see the little dialogue where I can select the month and date, we can get that lower and lower. And here it's only 5, so we can optimize it like that. So you have a transfer window, and it can give you a transfer window. The transfer window is not going to be a Hohmann transfer because this is a totally different sort of trajectory. It's basically trying for a straight line trajectory. Your peak cruise speed is 37 kilometers per second. So, and I think that's on top of the speed around the sun. So, that's the idea. The result of all this is some of these numbers are probably wrong because it's still using an approximation. It's trying its best, but it's still using an approximation. But the sort of fundamental idea that I was trying to get at when developing this calculator, that there is an optimal mass ratio in particular, and that there is a bottom to this. And here it really doesn't make, when it comes to Mars with a 100 megawatt system, you could easily lean over here and it won't make too much difference. You're gonna get there in 51.59 days. If we had much less fuel, we're getting there in 52 days. So you might as well not carry that 100 tons of fuel, even though we say that the optimal is at mass ratio of 4. If you did have the mass ratio of 2.87, which was our initial estimate, you're losing maybe a day at most, and you've saved yourself probably an extra launch, right? What you need in the system is a 2.8 kilonewton engine that gives you 7,090 seconds of ISP, assuming you have a 100 megawatt system. So, yeah. 100 megawatts is a lot, though. You're probably gonna have trouble getting that in 100 tons with the radiators and all that business. So that's the trick. Anyway, that's the power limited transfer calculator. The link will be in the video description, but I thought to share this result where we can actually optimize our ship for the trip time, because after that, the extra propellant is just going to slow us down. So we have limited acceleration, and that doesn't help anything. It just increases the trip time. And of course, if we have too little propellant, that increases the trip time because we can't accelerate fast enough. We spend a lot of time coasting. So that is why the curve looks like this. All right. So with that, thank you for watching. I hope you enjoyed this video. If you did, please do press like. If you have any comments or suggestions, please leave them in the comment section below. And I'll see you next time.